We're now going to take a look at the implementation of the Java monitor object coordination example. And this will be demonstrated again in the context of the simple blocking bounded queue program that's available in my GitHub repository. So this particular class, the simple bounded blocking queue class, provides a very simple synchronized blocking queue that's limited to a given number of elements. So you can only have up to n of them, where that's something that's set, or a capacity that's set in the constructor. And so let's take a look at simple bounded blocking queue. As you can see here, this implements simple blocking queue, the interface, and it will define some fields, which of course is the shared mutable state that has to be protected against race conditions. No surprise there. And naturally, we'll protect it against race conditions by using synchronized statements. Here's the constructor. The constructor will go ahead and initialize the capacity, and it'll initialize the new array list. So we'll have an array list implementation, and we'll have a capacity. And you never have to worry about putting any locks in the constructor because they're never called. A constructor is never called concurrently in multiple threads for the same object. It's only called in one thread for an object, and that's used to initialize it. Okay, so now let's go ahead and talk about the use of guarded suspension here. And to do that, we'll start with the take method. And you can see that the take method will be called by a thread. Let's say it's called by thread T1. And that will acquire the intrinsic lock and then wait while the queue is empty. In this particular case, we're going to use a synchronized method as opposed to a synchronized statement, just to be different, just to show you can do it different ways. In this particular implementation, it doesn't really matter. It's just a little bit more syntactically concise to use synchronized methods. You can see that we check to see if the list is empty, and you'll notice that the isEmpty method also is synchronized. And as you can see, this demonstrates the fact that synchronized methods use an intrinsic lock that has reentrant semantics. So if that wasn't the case, then when we called isEmpty, it would deadlock on itself. So we're perfectly fine here, even though it's a little bit more overhead than we might need. We probably should have an internal method called isEmpty impl or something that doesn't acquire the lock, just to avoid having to reacquire the reentrant lock. But this works perfectly fine. Now, something else that's important to remember, and this is almost always universally true, wait should always be called in a loop that checks whether the condition is true or not. And that's, again, because of the inherent non-determinism of concurrency and some other things having to do with so-called spurious wake-ups that we'll talk about in a second. So the reason why you need to call things in a loop is because you can't assume that even though you've been notified that your condition expression is to your liking. And that, again, has to do for various reasons, but not the least of which is notify all is being called all over the place here because of the limitations with Java built-in monitor locks. And therefore, or monitor conditions, rather. And therefore, you may be awakened an awful lot of the time when there's no possible way you can make any forward progress. So this, again, is due to the inherent non-determinism of concurrency and also because of those weird, spurious wake-ups we talked about before. Take a look at the link at the bottom of the page to learn more about spurious wake-ups. Basically, what happens there is in some multi-core, multi-processor implementations, you'll have wake-ups occur even when nobody called notify. And so, therefore, you just have to check that condition to make sure you don't try to keep making progress when, in fact, you don't have the resources that you expected. So, once again, a thread that's blocked on wait won't continue until it's notified that the condition expression that it's waiting on in its guard may be true. And the emphasis here is on may be true. So here's an example where we're calling put, and you can see that put is going to also have its guarded suspension, and when it is called and there's not a full queue, it's going to add the element to the queue, and that will, of course, then allow anybody who's calling take to be able to make forward progress. As you can see here, once again, put has the same pattern of guarded suspension that take does. We wait while the queue is full, and as before, the isFull method is also synchronized, and that once again illustrates the fact that the intrinsic locks that are part of Java built-in monitor objects are in fact reentrant or recursive. When thread T2, which is calling put, is able to add something to the queue successfully, it will then call notify all, and that will end up waking up thread T1 that's blocked in its call to wait. And again, we're using notify all here due to the fact that a Java built-in monitor object only has a single wait queue, which is a limitation. So when a waiting thread is notified, so for example, if the put method calls notify all, that will cause take to wake up. So it wakes up and it reacquires the lock. Then it has to reevaluate the condition expression. If the condition expression is still true, we have to keep, like, while it's still empty, we have to go back and wait again. If it's false, we got our resource, in which case we go ahead and notify everybody else that they need to wake up because the state has changed. And then in this case, we return the first element in the list, which is the one that's been waiting there the longest. And then the last thing, as we leave the synchronized method, the critical section, that releases the monitor lock, the implicit lock, and anybody else can then get into that critical section and do their thing, depending on the state that they find once they get in there. So that's the end of our discussion of the Java monitor object coordination example. And we'll come back and talk about some of the pros and cons of monitor objects here very shortly.